Go ahead.
Ready? All right. Plate tectonics, volcanoes, earthquakes. Take two. Last one didn't work. Irrigation. Try this again. All right. So I'm going to give you guys a summation of all three things put together. I'm going to give you guys a project here probably tomorrow or the next day. And then the last project we do on this unit, we'll move to earth chemistry, minerals, and rocks next week. So we'll just try and tie all this stuff together. So the very first thing you need to know with all three of these is you need to know the interior of the earth. You need to know the inner core, outer core, mantle, little line right there is the asthenosphere, lithosphere, and the very top one's the crust. You need to know the interior of the earth for sure. You need to know the crust and the lithosphere put together is a plate. The approximate thickness of that is going to be about 100 miles. These plates are huge. 100 miles thick, upwards of 5,000 miles long, 5,000 miles wide. You need to know that convection cells is what moves these plates. Convection cells is hot rock, moves and then falls, hot rock that moves and then falls. It's really the falling of this that drags the plates. It will crack the plate and then move it, and then move it. Without convection cells, you don't have plate tectonics. That's just the bottom line. So it'll actually move these plates. You need to know the three main ways that the plates move. The first wave that we'll talk about when the plate's moving, we'll talk about divergent. Moving apart. Middle of the ocean, you're going to get a divergent plate boundary. It wouldn't be an ocean if it wasn't divergent. You got magma coming up, it's burbling out, making a mid-ocean ridge. You get water on the edges, you'll have the continental crust. Continental crust is lighter, which is the reason why it's higher. The magma that's bubbling out here has more iron and magnesium in it, so it's heavier. That's making the ocean bottoms. Second one we'll go ahead and do is transform. Transform our side-by-side movements. Going one way, going the other way. Those plates are rubbing together. Remember, that's 100 miles that are rubbing together. They get stuck. When it breaks, that's what causes your earthquakes. There are no volcanoes with this at all. Convergent is the third one. There are two types of convergent. You can have subduction, which is going to make a volcano, and you can have two continental plates hitting each other head to head, which will make folded mountain range. Appalachian Mountains, Himalayan Mountains, two continents hitting each other. These are the different type of plate movements that you can get, and this is really the heart and core of what plate tectonics is. How do you know that plate tectonics is real? How do you know that it isn't just something we're lying to you about? Well, the easiest way is just look at the evidence that you guys have already did. Number one, South America fits with Africa, or it looks like it does. And again, when we talked about it before, it showed you the Mesosaurus fossils that they were finding on both continents, on both sides. That's a short-legged little reptile. It couldn't have swam that Atlantic Ocean, therefore they had to be together. By the way, guys, I don't know if it said it or not, but they found hundreds of these fossils on both sides. Approximately 100,000 animals have to die to make one fossil. It's a specialized environment to make a fossil. So these were definitely together. The coal that is found in North America and in, say, Britain, coal only forms in tropical environments, therefore these continents had to been over the equator. The glaciers that moved in both Africa and South America, again, it has to be cold, Therefore, these continents had been cleared down here in the Antarctica to make glaciers. The Appalachian Mountains that are found in Britain and Norway. Again, of course, they had to separate on that. Mountains aren't going to swim in the ocean. Probably one of these are all pieces of evidence, of course. Probably one of the bigger pieces of evidence is the amount of earthquakes and volcanoes that you find on plate boundaries. All the red is earthquakes, and all the yellow is volcanoes. You're only going to get those where you got divergent or convergent in terms of volcanoes. You're going to get more earthquakes where you got transform or you got subduction. And again, you've got subduction, the Pacific Arc, Ring of Fire. You've got it where you've got subduction here as well. So I mean, that's where you're going to get all your earthquakes. So those are all pieces of evidence for plate tectonics. It's real. I mean, it's only moving an inch a year in North America. You know, the thickness of a piece of paper, probably a day. But yeah, they're moving. Remember, these things are huge. They're 100 miles thick, maybe 5,000 miles long, 5,000 miles wide. I mean, these things are monsters. So they're not going to move too darn fast. That's pretty much plate tectonics in a nutshell. Plate tectonics, of course, will tie into volcanoes. You get your main type of volcanoes that go right along with your main type of plate boundaries. You've got divergent, is going to make a shield volcano. That's going to be hoi hoi lava. It's going to flow a long ways before it solidifies, and you get the magma that's coming out right here. You're going to find this on divergent plate boundaries, or an intraplate volcano if the plate itself, in other words, a hot spot, is an oceanic plate, which is what Hawaii is. So you have divergent for shield. Transform will not have volcanoes at all. That's going to be an earthquake. Convergent is going to make composite volcanoes. Composite. And you're going to get composite where you get subduction. It'll subduct maybe 200 kilometers before it starts to melt. Once it melts, it's less dense, so it'll come up, booming, boom, boom, and make your volcano. Composite meaning the compilation of two things. You're going to have a compilation of ash and lava. Lava is very viscous, has a lot of silica in it, so it's glass, so it's sharp. Hurts your feet if you walk on it. These are very explosive. Shield volcano is going to be Pahoehoe. Lava flows a long ways, very viscous, very little SiO2, so it's going to take a long time for that to solidify. The last volcano that you can get is something called a cinder volcano. You can actually find cinder volcanoes, small ones, on the side of composite. They're not very big, 500-600 feet tall, maybe half mile wide. And you can get little cinder volcanoes even on the side of the shield as well. One of the main places you can find these is intraplate continental, where you get a hot spot directly underneath. It'll form a little volcano. Say Arizona's got a bunch of them. Mexico has a bunch of them. And again, these are basically just what the name says. They're cinders, ash, pieces of rock. They can't get very big. They're like a big sand pit or a big sand pile or something. They don't get very big. Some of the other things you should know about these is that composite is the most explosive, the most dangerous. This is where you're going to get lahars. The snow and the ice will melt. It's on the top of the volcano. When it explodes, you get a Mongol mud flow that comes flowing down. Composite also going to be the one where you get huge pyroclastic flows. Hot ash and gas that comes rolling down off the mountain, it'll either incinerate you or suffocate you. These two right here are with composite. You can get a minor pyroclastic with these, but mostly it's just ash and a little bit of gas. Again, you can get some ash and gas with this, but not very much. I guess maybe it's possible to get a lahar on one of these. Usually these shield volcanoes don't get tall enough to get snow. Usually not enough to make a mud flow either. Most certainly these don't get tall enough. You should basically know the sizes of these things. Shield volcano can be 100 miles wide. Long ways. Here to Raleigh. They can be up 2 miles thick. Composite is going to be 2 miles high. About 20 miles wide. Pretty darn big. Here at Greensboro. Cinder cones are pretty small. Maybe 600 feet tall. Maybe a half mile wide. And that's probably even bigger than what it probably would be, but it might get that big. These things are pretty small for shield, composite, and cinder. The basics you should know about these: cinder or shield, I mean, is going to be in the center of the United States or the ocean, say Iceland, which is just a mid-ocean ridge of recent surface, or any of these are divergence. Composite is usually along the edge of continents, though you can get what's called a volcanic arc, like the Aleutian Islands or Japan, which is just oceanic, subducting underneath oceanic. And cinder, like I said, Arizona, Mexico, probably Africa has them as well. That's pretty much your basics with volcanoes. So the volcanoes tie in with plate tectonics. The last thing we really need to cover is earthquakes. Earthquakes, again, are usually more transform, though you can get earthquakes with both of these, convergent and divergent. A couple of the big things you need to know about earthquakes is you should always know the 3 different waves for earthquakes. If you get an earthquake that hits a seismogram, you'll get a seismograph that looks like one of these heart monitors. You should know the 3 earthquake waves. The first one's a P wave, second one is S wave, last one, and not all earthquakes will have it, will be your L wave. This is your fastest one, obviously, because it hits first. That's your push and pull wave. Your S wave is your side-to-side wave. Your L wave is a rolling wave, like an ocean wave. And if you get one of these will knock down your building for sure. Either way, they'll measure the highest amplitude on your waves to get the magnitude of the earthquake. The bigger that biggest wave is, the bigger the magnitude is. Magnitude are on a logarithmic scale, which means they go up by 10. It takes about a 2.0 to feel it. A 3.0, you can definitely feel the movement. 4.0, it'll probably break the plaster. 5.0, probably start breaking your chimney, actually. These go up 10 times every time. So 5.0 is 10 times 10 times 10, 1,000 times bigger than a 2.0. 10,000 times bigger is a 6.0, and so on. Once they start getting above 5.0, you're looking at problems. You got your building probably falling down under there. Which brings up the second point. If you guys are living in an area where you're going to have an earthquake, A, you should have your house built, make it earthquake proof. B, you should have earthquake insurance. And C, you should get out of the stinking building if you feel an earthquake. In other words, you feel a bump, if you can get out, go outside. Get away from the building, because fallen stuff is what usually kills people with earthquakes. Fallen trees, fallen bricks, whatever it is. Get outside. Once you get outside and have an earthquake, stay outside, because there's going to be aftershocks that come along behind it. You go back in to see what got broken, aftershock hits, well, then something else could fall into get you. These bad earthquakes, 5.0, 6.0 are pretty bad because you can't get an ambulance to you because the roads are broke. Fires usually start because the gas lines break and there's no water to go ahead and put out regular wood fire anyhow because the water lines are broke. So earthquakes they cause some problems, there's no doubt about that. Again, earthquake is just rock breaking and earth shaking. You got 100 miles on both sides of those plates. You get a full mile of rock that breaks, you get a lot of shaking and you get problems. You should know that the focus of an earthquake is where the rock actually breaks. Say that's the focus. The epicenter is the point directly on the surface of the earth above that focus. That's the point they'll look for in order to go ahead and find out where the earthquake actually occurred. You should remember how these things are found. They'll record the time on the P and the S wave when they hit on these seismographs. If this P wave hits at 9 o'clock, the S wave comes along 2 minutes later, hits at 9:02. They'll go ahead and record that on a P and S graph, and they'll figure out how many miles away that earthquake was from the seismogram station. So we'll put the time here on the side, 1, 2, 3 minutes. Graph curve looks like this. We'll put 100, 200, 300 kilometers away. If it was 2 minutes away, they'll follow it over, they'll follow it down. If it was 250 kilometers away from Raleigh, they'll put a circle around it. If it was 500 kilometers away from Charlotte, they'll put a circle around it. Say it was 100 kilometers away from Greensboro, they'll put another circle around it. Wherever the 3 circles intersect, that's where the epicenter is. So it takes at least 3 circles. They'll use more than 3, but 3 is the bare minimum. If they tried to use 2, it could be either here or here. 3 is where all 3 intersect, and then you could figure out where it is. Couple last things about earthquakes. Earthquakes can cause tsunamis. Usually you're only going to get a tsunami where the plate is subducted. Whoop. Get a plate here, whoop. We'll thicken it up. As this plate subducts, it might bend this plate. Rock will actually bend if you put enough stress on it. If that thing will break, it'll flex underneath the water. You'll get a big wave that comes on stream or on land. You guys see a tsunami? What'll happen? All the water will flow away, and then you'll look way out and you'll see a thin line, which is the wave that's coming in. Yeah, we'll turn and run upstream, or run uphill, or get the car, better yet, and drive away from the ocean, or get in a cement structure that won't get knocked down by the wave, which is how they survived in Indonesia when it hit. Occasionally you can get a underwater landslide of mud and rock. That can cause a tsunami as well. That does happen. Usually from an earthquake that shakes it and flows it downhill. That happens occasionally on these. I think on the outline I gave you guys short-term predictions for earthquakes and long-term. Well, neither one of them really work. Occasionally people have said that before the earthquake hit in Indonesia, the elephants people were riding actually turned and ran uphill before the tsunami even hit, so they were able to sense it. But people say that chickens will actually fly up and roost in trees beforehand, or dogs will bark beforehand. I don't know. The one that we had here a week ago, my dog didn't bark beforehand. Barked after the earthquake hit, but not during, so that one didn't really work. Long-term predictions is they'll go by gaps in the record. If an earthquake seems to hit every 30 to 50 years, they'll give you a percentage. They'll say, well, there's a 50% chance of a 5.0 earthquake hitting in the next 9 months. It doesn't give you a whole lot to play on. How you do anything about that? You have earthquake insurance and a bug-out earthquake bag in case an earthquake hits and you got food and water. But I mean, it doesn't really work. But, That's pretty much sums up, I think, plate tectonics, volcanoes, or earthquakes. Like I said, I'll give you guys a project here, probably in the next day or two. And then we'll go to rocks and minerals and earth chemistry next week. Thank you.
All right.